Welcome back, business calculus students. In this video, we're going to pass that halfway mark on our final exam review worksheet. I'm going to work all the problems on page 4, numbers 14 through 16. So on problem 14, it says, given the function f of x, find the following. First, the critical numbers. If you'll recall, the critical numbers are those potential points where we may have a relative maximum or a minimum. They occur where the derivative is equal to 0. This indicates that whatever our function happens to look like, we have a slope of 0. So let's first find the derivative. This is a polynomial, so we can differentiate term by term. The derivative of 8x cubed is 24x squared. The next term, we have negative 18x squared. Its derivative is going to be negative 18 times 2x, which simplifies to minus 36x. The next term is negative 240x. The derivative there is simply the constant, negative 240. And the derivative of plus 4, the constant, is 0. Now, we want to set our derivative equal to 0 and solve for x. This will produce the critical numbers. Notice each of these terms in our derivative has a common factor of 12. So let's factor out the 12. That's going to leave behind 2x squared minus 3x minus 20. This makes our numbers a little smaller and easier to work with. Now I can factor that remaining trinomial. It factors as 2x plus 5 times x minus 4. Notice the outside terms there are negative 8x. The inside terms plus 5x. That gives me the correct net middle term of negative 3x. And of course, the first and last products are correct as well. Now, I'm going to set each factor equal to 0 and solve for x, except for this little constant. 12 equal to 0 would not make sense. So ultimately, I can ignore that constant coefficient. I'm going to set each of these little factors equal to 0 and solve for x. Looks like one of our critical numbers is negative 5 over 2, and the other one is 4. So we have two critical values. That means points where we might possibly have either a relative maximum or a relative minimum. Part B says find the open intervals where the function is increasing, and notice part C, decreasing. So I'm going to do all the work here in the space for B, and this is going to help me to answer both B and C. What I want to do is form a number line and put both of my critical numbers on this number line in numerical order. So negative 5 over 2, somewhere over here, 4, somewhere over here. This is going to divide our space up into 3 sections. Then I'm going to test the sign of the factors of my derivative on each interval. Notice the factor 12 is always positive. It's not going to change the sign of our derivative, so again, I'm going to ignore that 12. But the other two factors each have a variable, so it's possible that they change sign. So I'm going to list my two factors here on the left side of my sign graph. Then, in the intervals between those critical numbers, I'm going to choose test points, plug them into each factor, and judge their sign. So I need a test point somewhere left of negative 5 halves. Remember, negative 5 halves is about negative 2.5. So I'm going to use the test point negative 10. Okay, so if I plug negative 10 in for x in my first factor, 2 times negative 10 plus 5 is negative 20, plus 5 gives me negative 15. I'm not really concerned about the value, I'm just looking for the sign. If I plug my test point, negative 10, into the second factor, I'm going to see its sign is also negative. Now remember, our derivative up here is formed as the product of these two factors. A negative times a negative would give me a positive. So on that interval, the derivative is positive. That means the original function is increasing. Okay, let's repeat that process for the second section. I need a test point between negative 5 halves and 4. I'll use the test point somewhere in here. How about 0? So I'm going to plug 0 into each of these factors that I have listed here on the left. If I plug 0 into 2x plus 5, the result is positive. And then 0 minus 4 would give me negative. Positive times negative is negative. So my derivative is negative on that interval. That means my original function is decreasing. Finally, in the last section, we need to choose a test point greater than 4. Remember, any test point greater than 4 represents behavior on that entire interval. So I'm going to use the test point 10. When I plug 10 into both of those factors, I find out the result is positive, and a positive times a positive is a positive. Now I can see that my function goes from increasing to decreasing to increasing. So it does look something like our little hypothesis here. So where is the function increasing? It's increasing where my derivative is positive. So I'm going to read my graph from the left to right. Okay, the leftmost value where my my derivative is positive, well, it goes on to the left forever. So we're going to read that as negative infinity. Then it goes up to our critical number, negative 5/2. I'm going to use an open interval because remember, at negative 5/2, the derivative is 0. It's not positive. Then in between, it's negative. So I'm going to skip over here to the other positive section. It's going to start at 4 and go to the right infinity. That U there simply means union. That means I'm uniting those two intervals to show everywhere where the derivative is positive or the function is increasing. To answer question C, I'm looking for where is the function decreasing. It's going to be decreasing where my derivative is negative. That's right here in the middle. If I read that left to right, using open intervals or parentheses, I get from x equals negative 5/2 to x equals 4. So if I were to graph this on my calculator, I could observe that it would be increasing, then it would be decreasing, and then it would be increasing. Again, a lot like this little sketch we drew. Okay? Let's move on to problem 15. Suppose a certain drug is administered to a patient with the percent of concentration of the drug in the bloodstream t hours later given by k of t, where 0 is less than t is less than infinity. So t is the number of hours, and the concentration of the drug is this k function. This part simply means that t starts at 0 and goes on indefinitely, okay? On what time intervals is the concentration of the drug increasing? And then on part B, on what intervals is it decreasing? So really, I'm going to be doing the same process that I did on problem 14. I'm just using a different function. So what do I need to know in order to answer this question? I need to know where the derivative is positive and where the derivative is negative. All right, so first step, find the derivative. Notice the original function is a quotient of two functions of t. So I'm going to find the derivative using the quotient rule. Good practice here. Let's square the denominator. Lead with that term in the numerator, multiply by the derivative of the numerator, minus derivative of the denominator times the original numerator. I definitely want to simplify this because remember, I need to find critical numbers. That means I need to set it equal to 0 and solve for t. So simplifying the numerator here, let's just go ahead and distribute 20 times t squared, 20 times 25, and then we'll multiply here as well. So we have 20t squared plus 500 minus 40t squared, whoops, divided by t squared plus 25 squared. Okay? Simplifying, we end up with k prime of t to be negative 20t squared plus 500 divided by, and again, leave your denominator in this factored form. Now, we're going to be analyzing the sign of this derivative. It's best to have it in complete factored form. So in the numerator, notice we have a greatest common factor there of negative 20. So I'm going to factor out the negative 20. That's going to leave behind t squared minus, what? Can we figure it out? Is it 25? 500 divided by 20 is 25, okay? And the denominator will stay as is. Now, what I want to do is set this equal to 0 in order to get the critical numbers. Notice when I set this equal to 0 and then cross multiply, I'm going to be able to cancel out that denominator completely. Okay? Think, multiply both sides by the denominator. It's going to cancel on the right and 0 out on the left. So we end up with 0 equals negative 20 times t squared minus 25. Divide both sides by negative 20. It cancels on the right, zeros out on the left. Almost there. Add 25 to both sides. And notice we get t then equals plus or minus 5. Okay, now remember, t represents time in hours. And this restriction said I'm just going to consider positive time. So I'm only going to consider positive 5 when I look for where the function is increasing or decreasing. Okay, so quick review. We found the derivative using the quotient rule. We set the derivative equal to 0 and we solved for t. We came up with two critical values, but I'm only going to consider the sign of my derivative on that interval 0 to infinity. Okay, so I'm going to put my left stopping point over here at 0. Again, that comes from this original restriction. The only critical point I'm going to consider is t equals 5. Remember, negative 5 is over here somewhere, but because it's not in our domain, we're not going to look that way. Okay? I'm interested in the sign of my derivative. The best form to consider my derivative, right here. Okay? And in fact, we could break it down even further. Notice that t squared minus 25 could be factored as t plus 5t minus 5. Okay? So what I can do is list all of the factors of my derivative over here on the left side of my sign graph like we did on the previous problem. One of those factors is negative 20. I am going to consider this constant this time because the negative will affect the sign of my entire derivative. I also want to consider the two factors I broke down, t plus 5 and t minus 5. And just for illustration purposes, I'm going to go ahead and put this denominator, t squared plus 25 squared, on the graph. Ultimately, you can leave that off of the graph because since I'm squaring it, it's always positive. So this one is always positive regardless of the test point I'm plugging in, and that constant negative 20 is always negative. So to test the signs of the other two factors, I need test points. Let's choose first of all a test point between 0 and 5. 1 would certainly work. If I plug 1 into this first factor, t plus 5, I find out it's positive. And 1 minus 5 is negative. Okay? Now, looking at the form of my derivative over here, I can see everything's being multiplied or divided. So if I take a negative times a positive times a negative times a positive, because I have an even number of negatives there, I observe that the result is positive. Okay? Let's pick a test point greater than 5. Any number greater than 5. How about 10? If I plug 10 into this one, it's positive. 10, into this one it's positive. Now I consider a negative times a positive times a positive times a positive. That result is negative. Now I can answer the questions. Remember, part A, we haven't answered part A yet. It says, where is the concentration increasing? It's going to be increasing where my derivative is positive, and I'm always going to express it as an open interval. So the drug is increasing between the administration at 0 hours until 5 hours later. So the patient takes the drug, it's sent into the bloodstream, and the amount in the bloodstream increases for 5 hours. On what interval is it decreasing? Well, the derivative went from positive to negative, so it's decreasing beyond that time, from 5 hours until indefinitely. Your body begins to metabolize the blood and reduces the amount in the bloodstream. Okay? So really the same problem we did on number 14, we just had to think a little harder, dealing with the quotient rule, realizing we needed to find those critical values without being asked to, figuring out the sign of our derivative and interpreting that as increasing and decreasing. All right? If you run out of space, feel free to spill your work over on the back side. One more problem for this video. Let's look at number 16. Consider the function f of x equals x squared plus 3x minus 5. Find the x value of all points where the function has any relative extrema. This can be maximums, this can be minimums. It's not specifying. It just wants us to give potential relative extrema. All you have to do is think about what's being asked here. It's saying, what are the critical values? That means I need to solve f prime of x equal to 0. So I'm going to begin by finding the first derivative. Yes, you're welcome. I just gave you a simple polynomial on this one. So our first derivative is 2x plus 3. We set our derivative equal to 0, and then we solve for x. Divide both sides by 2. We would end up with x equals negative 3/2. We don't know at this point if this is leading to a maximum or a minimum. It's simply a potential location for a maximum or a minimum or a relative extrema. If it's a max or a min, how would I find the value of that max or min? If I want to find the value, I'm going to go back to the original function and calculate the function value. Okay, remember, if I take negative 3/2 and I plug it into the derivative, it's going to tell me 0. It's simply telling me the slope is 0 at that point. So notice, you can check this on your calculator. We're looking at a parabola. We have located the x value of the vertex. The slope here is 0. That means I have a horizontal tangent line. So I'm simply calculating the y value of the ordered pair location of this relative. Now we can see it's a minimum, but in general, an extrema. So plugging negative 3/2 into the original function, looks like we're going to have to calculate a bit here and simplify. So negative 3/2 squared, square the top, square the bottom. On the second one, we have 3 times negative 3/2. That gives me negative 9/2 minus 5. Let's grab a common denominator of 4. Here, if I multiply the denominator by 2, I better multiply the numerator by 2. And 20 over 4 here gives me 5. 9 minus 18 is negative 9. Negative 9 minus 20 is negative 29. So we end up with negative 29 over 4. All right, keep studying, hang in there. We have a few pages to go.